this lesson, we'll discuss single and multi-index models. We'll start the discussion with the rationale and intuition behind these models, which leads to a simplifying correlation structure. First, we'll discuss the expected return and risk characteristics of individual securities. Subsequently, we discuss the portfolio characteristics in the presence of single index models. We'll also understand the index models with the help of a simple example. We'll examine the role of beta, that is sensitivity of the portfolio towards these indices. Next, we'll introduce multi-index models. We'll compute the expected returns and risk for individual securities, and then we'll derive these for portfolios. Single index models and correlation structure. In this video, we'll introduce single index models, their correlation structure, and compare them with a situation where there is no simplifying structure is assumed. We'll begin with the two equations that provide the base to all the analysis in portfolio management. These are the equations corresponding to portfolio returns, which is this one. Portfolio returns RP bar equal to sigma xi Ri bar, and standard deviation. These notations are familiar to us. Sigma p square is equal to summation xi square sigma I square plus summation xj xk sigma jk. Here RP bar is the expected return on portfolio, xi is the weights, Ri bar is the individual security expected returns, sigma p square is the variance of portfolio, sigma I squares are the variance of individual securities, and sigma jk is the covariance between security j and k. Now, for the analysis of portfolio and examination of efficient frontier, three key inputs are required here in these equations 1 and 2. First is the expected returns for each security, which is Ri bar, standard deviation for each security, which is sigma I, and correlations across each pair of security, which is either you can say rho jk correlation or covariance sigma jk. Correlation is just a standardized form of covariance. So now if an analyst is following 150 stocks, they need to prepare 150 estimates of expected returns. So 150 estimates of expected return, Ri bars, 150 estimates of standard deviation, that means sigma is. But the correlation structure and correlation requirements are much intensive, that means rho jk's. And for example, if you have n stocks, you need n into n minus 1 upon 2 correlations. For example, here you have 150 stocks, so you need 150 into 149 upon 2 correlations, which is 11,175. So we need 11,175 inputs for correlation coefficients. This kind of mammoth nature of correlation coefficients has motivated researchers to look for correlation structure across securities to simplify the analysis. How? Consider n variables to track. It is difficult, but if one finds that 90% portion of these variables is explained by one single variable or one single index in this case, then you only need information about that one variable to predominantly define or get information about all the n variables. And this leads to the genesis of single index models. That means the observed covariances essentially reflected the correlation structure between that index and these securities. This search for correlation structure across securities has led to an important set of models called single index models. These models assume a single common influence that impacts or affects a large number of securities simultaneously in a similar manner. The single common factor is responsible for the co-movement of large number of securities, thus simplifying the correlation structure to a large extent. The model is based on the evidence that most of the stocks follow market movements to a certain degree. For example, when market goes up, a large number of stocks go up and vice versa. This leads to the genesis of single index models, where market index such as Nifty or S&P 500 acts as the proxy of the single index, that is market index. Therefore, and hence the returns on a security can be described by a single index model with this equation. Here Rm is the return on market index, Ri is the return on the security, Ei is the error term which is specific to the security, beta is the constant which measures the return in Rm for a given change in Ri, For example, a beta I of 2 would indicate that 1% change in market would cause 2% change in stocks return. Again, this AI is also the return part of return that is unrelated to market performance. So this AI and EI are two components that are not related to market. EI can be written as or said to be the random probabilistic element of the stock return with the expected value of 0. So expectation of EI is 0 or EI bar is assumed to be 0 here. To summarize, in this video, we examined how the assumption of single index models simplifies the correlation requirements considerably. We also discussed how these single index models help us define the expected returns from a security in the form of a single influence or single factor like market in a more simplistic manner. Construction of single index models. In this video, we'll provide the definition of single index models and various aspects related to that definition. The basic equation of single index models can be simply written as Ri equal to alpha I plus beta I times Rm plus Ei. Important to note that Rm and Ei are random variables. This Rm and Ei are random variables. Often random variables are defined by a probability distribution like a normal distribution with a mean and standard deviation. In this case, consider the mean of Rm and Ei as 0. So mean of Ei as 0 as we discussed earlier, expected value of Ei or mean of Ei as 0 and mean of Rm or expected value of Rm as Rm bar. And their standard deviations as sigma m and sigma Ei. We have also said that Rm and Ei are uncorrelated, and therefore if they are uncorrelated, therefore the covariance between Ei and Rm should be 0, or in other words the correlation between Ei and Rm should be 0, that is expectations of Ei minus 0 into Rm minus Rm bar should be equal to 0. Generally, this equation, this model is estimated with the regression analysis. In regression analysis, by design, to a great extent it is guaranteed that Ei and Rm are correlated, not correlated over the period of analysis. So over the period of analysis, this assumption to a great extent is held by the model itself, by the design or construction, we can say. However, there is one additional assumption of single index model that is not guaranteed by regression analysis. This is as follows. Single index model assumes that Ei, the error Ei, is independent of Ej for another security. Or more formally, one can say the expectation of Ei Ej 0 or correlation between errors Ei Ej is 0. This requires that the only reason stock should co-move is because of the market movement. There are no other effects like industry effects, etc., that can cause correlation across stocks. So there is nothing in regression analysis that ensures it. And therefore, the performance of the model depends on how close this assumption is to reality. This model Ri equal to alpha I plus beta I times Rm plus Ei under the assumption of single index model is assumed to represent the dynamics of all the stocks in the market. That is, if there are n stocks I equal to 1 and so on, 2, 3 and up to n, all those stocks, the return is expected to be defined by this single index model. Generally, it is given that or assumed by default that the single index would be market factor, because market factor, there is a wide evidence that market factor affects most of the stocks in the market systematically. Let's now define the single index model. Basic equation of single index model we have already seen. This is the basic index equation. Under the assumption of single index model, this equation is assumed to represent the return dynamics of all the stocks in the market. Now, by design, or you can say by construction of the regression model, the mean of error term or residual term is 0. This is by design ensured by regression model. Then by assumption, the index is unrelated to the idiosyncratic component, which is Ei or the error term, that is expectation of Ei and market is 0. That means market returns and error terms are not correlated. There is no correlation between error and market or residual or stock specific term and market. Also, securities are only related to each other through the index, which is market. That is, there is no correlation across securities between two stocks. Between two stocks, the residual terms or stock specific term, there is no correlation or covariance, in other words. However, this assumption is not ensured by regression model, as we discussed earlier. Also, by definition, we define the variance of error term or stock specific residual or stock specific component of return as sigma ei square, and the variance of market is defined as sigma square m. Now that we have boundary conditions, we can derive the expressions for expected return and standard deviation and covariance easily. Expected returns under the single index model can be easily obtained by this expectations operator on Ri. Expectations of alpha I plus beta I times Rm plus Ei equal to expectations of alpha I separately plus expectations of beta I times Rm plus expectations of Ei. Now expectations of Ei is 0, we already discussed that. Since alpha is constant term, so expectations of alpha I will be alpha I itself, and expectations of beta I times Rm should be beta I because beta is a constant, and Rm bar. Rm bar is the expectation of market return. So this is our single index model, expected returns definition for single index model. Coming to standard deviation of return can be easily given by this formula. Sigma I square equal to expectations of Ri minus R bar raised to the power 2. Now we can extend the expression for returns, the return definition here, which is alpha I plus beta I times Rm plus Ei, and Ri bar we already know alpha I plus beta I times Rm. Simplifying this expression, we get expectations of beta I times Rm minus Rm bar plus Ei raised to the power 2. This can be expanded in the form of a plus b whole to the power 2 equal to a square plus b square plus 2ab. In the similar manner, we can expand this expression, and here please note we'll obtain this expression beta I square expectations of Rm minus Rm bar raised to the power 2 plus expectations of Ei square, because the third term, which is expectations of Ei times Rm minus Rm bar, will be 0, because by assumption there is no correlation between Ei error term and market term, and to a great extent this is ensured by the regression model as well. So the resulting expression for standard deviation becomes sigma I square equal to beta I square times sigma m square plus sigma I square. Notice it does not include a common term, which is the error and Rm, because by assumption as well as to great extent by the design and construction of the regression model, there is no correlation between error and market returns. Lastly, coming to the covariance part, the covariance between two securities I and j can be easily defined as expectations of Ri minus Ri bar into Rj minus Rj bar. Further, again expanding for Ri can be expanded in this form by the single index model definition. Similarly, Ri bar can also be expanded with the definition of single index model. So we get the resulting term like this. This term can be further opened and simplified in these terms. Please notice across these terms, the expectation of Ei Ej is 0. This is by assumption. Regression model does not exactly hold this, but by assumption, since market is the only influencing factor, therefore there should be no correlation across error terms or idiosyncratic part of return. So this is 0. By design of regression model and by assumption, error terms are not correlated with market. So this correlation or covariance is also equal to 0. And same goes for this. So we have only this term remaining, which is beta I times beta j into expectations of Rm minus Rm bar raised to the power 2, which is equal to beta I times beta j sigma m square. This is the expression for covariance. To summarize, in this video, we discussed how the assumption of single index models results in the definition of return and expected return for a security. We also discussed how we can compute the risk or standard deviation and covariance between two stocks in the presence of or the assumption of single index models. And we saw how this kind of analysis considerably simplifies the correlation structure and results in a model where computation of risk and return is very simplified. Single index models with an example. In this video, we'll examine the application of single index models with the help of a numerical example. Consider the following example where we are given the actual returns and the beta for a stock and market returns. So you have beta equal to 1.5 and the actual returns are given here and the returns from market are given here. To perform this numerical, first we need to compute the average returns for the stock, which are computed here, the average of these stocks to get the average return, and we also compute the average returns for the market here. Once we have the average return for stock and market here, we can solve the model, which is the single index model alpha I plus beta I times Rm bar. We can solve this equation because we know here Ri, we know here Rm, we know the beta. We can solve this to get the estimate of alpha I. Once you have the estimate of alpha I, you can then have all the entities known here in this model, which is the actual returns Ri or predicted returns Ri minus Ai minus beta I times Rm. You have Ri known, this alpha I or alternatively Ai, what we are referring to, is also known, beta is known, and Rm is known. So you can compute the residuals also and define the model completely for each period. So using this equation, we can solve for Ai to get Ai as 2% or alpha I. am referring to Ai or alpha I interchangeably. Now that you have alpha I, you can estimate the values of Ai as we discussed. So while computing these values, we get these values of Ei for each of the periods using these Eis, and we can check here the average of Ei is 0 as we have assumed. A lot of it is ensured by regression model. You get average of Ei or Ei bar as 0. You can compute the variance of Ei as 2.8. So we have the variance here. Using these values, we can compute the variance of Ei, which is sigma square Ei. This is also the residual component of risk in the model. Now that you have the residual component of risk, you can either compute separately the overall variance, which is 20.8, which is the total risk, which includes the market part of risk as well as idiosyncratic part of risk. Also, you can cross check it by computing the idiosyncratic part, which is sigma square Ei, 2.8 separately, and market part of risk. Market part of risk is beta I square times sigma m square, which can also be computed. For sigma square m, you can compute the variance of market using these values, which we can compute variance of market, which is 8 here, and then you can multiply it by beta square, which is 1.5 into 1.5 into 8 plus 2.8, which is 20.8, which again we indirectly computed, and directly also we computed, and numbers are matching. To summarize, in this video, we understood the application of single index model for a given security. We also cross-checked the implications of applying single index model by directly and indirectly computing the values for risk and expected return. Portfolio characteristics with single index models. In this video, we'll discuss various portfolio characteristics such as expected return and risk in the presence of single index models. Now, with the assumption that the single index model holds, let us examine its impact on portfolio returns and standard deviation. The expression for expected returns on portfolios is provided by this equation: Rp bar equal to summation xi Ri bar, I equal to 1 to n. Assumption here is that this kind of single index models, which is Ri bar equal to Ai plus beta I times Rm bar, holds, where Ri is the expected return on security and Rm bar is the expected return on market. Substituting for this expression, the portfolio return expression becomes Rp bar equal to summation xi Ai plus summation xi beta I Rm bar. Also, the variance of the portfolio can be written as xi square sigma I square summation I equal to 1 to n, and summation I and j over xi xj xi sigma ij I not equal to j, where sigma ij is the covariance term and sigma I square is the variance of security I. Sigma ij is the covariance between security I and j. Now, substituting the expression for variance and covariance in the presence of single index models, as we saw earlier, the resulting expression becomes sigma p square equal to summation I equal to 1 to n xi square beta I square sigma m square plus summation I equal to 1 to n and j equal to 1 to n, where I not equal to j, xi xj beta I beta j sigma m square plus I equal to 1 to n xi square sigma I square. Looking at these equations of portfolio risk and return, it should be clear that we require estimates of alpha I, beta I and sigma I for each of the stock, and estimates of Rm bar and sigma m square for market. Now, if you need n securities, then 3n estimates for these 3 terms and 2 estimates for these 2 terms. Overall 3n plus 2. So if you believe that there are 150 securities that you want to track, you need 450 plus 2, 452 estimates, as compared to the 11,485 estimates when we did not assume any kind of correlation structure like single index or multi-index model. This is a very small requirement, a very simplifying structure that we have assumed here. Let's further simplify the portfolio expected return and risk expressions. We can define the beta of a portfolio, which is beta p, as weighted average of beta I of over all the securities where I equal to 1 to n. Similarly, alpha p can also be defined as summation ai into xi I equal to 1 to n. And therefore, the resulting expression for portfolio becomes xi alpha I summation over I equal to 1 to n and xi beta I rm bar summation I equal to 1 to n. And therefore, if I put this expression as alpha p and this expression as beta p, again rp equal to alpha p plus beta p times rm bar, which is very similar to the equation that we already saw, which is alpha I plus beta I times rm bar. Please note here in this equation, that if the portfolio under consideration is market portfolio, then alpha p equal to 0 and beta p equal to 1. That means rp bar is nothing but rm bar. Also, the stocks with beta p greater than 1 are said to be riskier than the market, and stock with beta p less than 1 are said to be less risky than market. Now, let us examine the risk of a portfolio using the equation we saw earlier, sigma p square equal to xi square beta I square times sigma m square plus I equal to 1 to n and j equal to 1 to n summation xi xj beta I beta j sigma m square plus summation I equal to 1 to n xi square sigma I square. Let's simplify this equation a little bit. We can combine these two terms so that this I not equal to j expression will be removed and this resulting expression is received, which is just a combination of these two expressions, and this expression remains same. Now again here we can replace this expression or divide this expression into these two components, xi beta I summation 1 to n and xj beta j summation 1 to n times sigma m square. Now please note that these are nothing but beta p. So this is also beta p, this is also beta p. And therefore the resulting expression is sigma p square times beta p square sigma m square plus xi square sigma ei square summation I equal to 1 to n. This is a very interesting expression of standard deviation for portfolio in the presence of single index models. Let us carefully examine this expression of portfolio standard deviation. The expression says x sigma p square is a function of beta p sigma m and xi square sigma ei square. If you assume that there are large number of securities and equal amounts are invested in them, that is x1 equal to x2 and so on equal to xn equal to 1 upon n, then I can further simplify this expression as sigma 1 upon n into sigma ei square upon n I equal to 1 to n. Now in this expression, if n is very large, then this expression tends to 0. This expression tends to 0, and therefore the stock specific or the residual component of risk, which is this, it approaches to 0 and only this expression remains. What it means is that the remaining risk, which is beta p square sigma m square, it is only on account of that single index or market. Irrespective of the risk of securities, the risk of a well diversified portfolio with a large number of securities is only determined by this market risk and the sensitivity of portfolio to this market risk. Here beta p is just a weighted average of individual security sensitivities, that is beta I is xi, so it's just a weighted average, this beta p. That means for a well diversified portfolio, what matters is the contribution of securities to the portfolio risk, which is how sensitive are the securities in the portfolio to the market movement. For example, consider a hypothetical situation. In a well diversified portfolio, all securities have beta equal to 0. Let's say beta is equal to 0. Then the risk of the portfolio will also be 0 in the assumption of single index model. So beta p is also beta i's are 0, then beta p is also 0, and therefore this sigma p square becomes 0. Therefore we are able to say that because we know that each security's contribution to market risk in this portfolio is 0, and residual risk, which is the diversifiable risk, which is also 0. Here beta p square sigma m square is the measure of portfolio's non-diversifiable or systematic risk, and therefore sigma m is independent of securities, and only the term beta p is dependent on the securities, and on average reflects the sensitivity of the portfolio constituent towards market risk. To summarize, in this video we discussed the expected return computation and risk computation of the security and portfolios in the presence of single index model, we found that the expression for expected return is quite similar to the one with single index model, which is Rp equal to alpha p plus beta p times Rm bar, which is very similar to the one we saw earlier, Ri bar equal to alpha I plus beta I times Rm bar. We also saw that the risk of a portfolio, the standard deviation, has two components, and if the portfolio is well diversified, the idiosyncratic component becomes zero, and the only component of risk that matters is the non-diversifiable risk, which depends on the market risk and the sensitivity of individual securities that contribute to beta p, or sensitivity of the portfolio to the market risk. Single index models, market model. In this video, we'll discuss a special class of single index models, which is market model. A less restrictive form of single index model, known as market model, has found wider acceptance. The only difference here is less restriction. Consider a single index model like Ri bar equal to alpha I plus beta I times Rm bar. Here, the assumption that covariance between Ei, Ej equal to 0, which was a very integral and central assumption of single index model, is relaxed or waived, and it becomes the market model. This simply means that there may be some co-movement across securities that are not due to the market. This is in contrast to the single index model. The relationship between the expected returns on the security and the market remains the same, which is this relationship. However, since the assumption of covariance is not the same as the single index model, we do not get the same simplified portfolio expression. What are the additional factors that may affect the returns of a security in addition to market index? In addition to this Rm bar, there can be industry specific factors, for example, industry, or factors, for example, international factors related to some international markets specific to regulatory changes, or certain niche factors which are not part of this market factor but still can affect the returns of a security. Market model allows the presence of these factors and says that there can be possibly these factors which can cause correlation between the error term, or autocorrelation between the error term between two errors like Ei, Ej, because of these factors like industry factor, and they may not be on account of market factor. So this is market model, which is a special class of single index model which assumes the covariance between Ei and Ej is not equal to 0. It can be non-zero. Estimation of portfolio beta with single index models. The discussion on single index model makes it amply clear that one needs to estimate beta. One of the simple and most commonly employed methods relies on the estimation of historical betas. Here we make use of this very simple index model RIT equal to alpha I plus beta I times RMT plus EIT, and we try to fit this regression model. These are the scatter points, these are our observations, and we try to fit this model RIT bar equal to alpha I plus beta I times RMT bar. We fit this regression model. The model can be represented in the form of this straight line. The slope of this line, which is beta I, is our estimate of beta. So we are fitting a line across these scatter points with simple, often used OLS, ordinary least square method of regression. So this is called method of ordinary least squares, and this slope of this line is the best estimate of beta over the period of examination. Now here, since we are fitting the line across scatter points of Ri, this is the RIT, or often called Ri. So these are the security I's return over different times, and RMT, which is the market return over different time t. We are fitting this line, and this expression we can observe Ri and Rm from the various databases which are directly available from exchanges or databases like Bloomberg. This plot of Ri and Rm will result in this kind of figure. The line fit between Ri and Rm observations available over time. And for drawing this straight line, like I said, we often use a measure called ordinary least square measure. The slope of this line is the best estimate of beta over the period of examination. Now, once you have this kind of expression, the value of beta is very easily computed in the form of this expression, which is nothing but sigma im, which is the covariance between security I and m, and divided by sigma square m, which is the variance of market. This is nothing but this RIT minus RIT bar into RMT minus RMT bar, summation over t equal to 1 to t, and RMT divided by RMT minus RMT bar raised to the power 2, summation over t equal to 1 to t. So this is the expression which is driven by this regression model. Now, once your beta is estimated, you can also estimate the alpha I simply by this equation, alpha I equal to Ri bar minus beta I times Rm bar. We can estimate alpha I from here. But these beta estimates are also subject to errors. Also, the fact that firm characteristics such as capital structure, industry, etc. change over time. Hence, firm beta is also expected to change. Generally, to make more accurate estimates of beta, analysis compute beta of portfolios. So we tend to work with beta of portfolios, not single securities, where portfolios are selected from specific industries. So these industry betas or industry portfolio betas are less noisy and more informative or more informationally efficient. So portfolio betas are less noisy and subject to less estimation error. Generally, these are computed for industry specific portfolios. This happens because the randomness that is specific to security averages out in the portfolios. For example, there may be some random variation that is upward in one security and downward in the other. Overall, this effect is cancelled out, and therefore historical betas of portfolios are often employed for future production of security betas. To summarize, in this video, we discussed the estimation of beta through ordinary least square method, where we fitted the scatter points. We fitted a straight line here. The slope of this fitted line between Ri, which is a security return, and market return, is often referred to as beta, which represents this kind of model, Ri equal to alpha I plus beta times Rm plus error term. The fitted line equation is Ri bar equal to alpha I plus beta times Rm bar, and beta is our slope estimate. Single index models beta example. In this video, we'll try to understand computation of beta in the presence of single index models. In our previous discussion on the similar example, we assumed beta to be given, but let's try to examine beta now. In the example, we have been given values of RIT, which is for these 5 periods. We have our return values, market returns for these same periods. So first, we can compute the average values of market return, which is 4%, and security return 8%. Their variances also, sigma m square and sigma it square, which is 20.8, sigma m square is 8. We can also compute the covariances with this expression, RIT into RIT bar times RMT minus RMT bar. So this is RIT minus RIT bar times RMT minus RMT bar, for which the values are computed here. And we can see the summation is 60. When we divide it by 5, we average it out to get the covariance number sigma m, which is 12. Now the beta is nothing but the ratio of this 12 divided by 8. So 12 upon 8, 1.5. This is my beta for the returns that are given here. So this is how we compute beta for any security where returns for the security and returns on the market are given to us. A few words on beta. In this video, we discuss some of the very important properties of beta. Essentially, beta is a risk measure that is estimated from the relationship between the returns of a security and that of the market. Since it is a risk measure, then mathematics apart, it should be linked to the firm characteristic and the risk profile of the firm. There are some of the very well-known variables that affect the risk of a stock. For example, dividend payout, asset growth, leverage, liquidity, asset size, earnings variability, accounting beta, and so on. We'll discuss some of these properties here. It is assumed that firms that pay more dividends have positive future expectations, and these firms are considerably less risky and therefore have low beta. These are called low beta firms, and therefore we can expect a negative relation between the firm beta and dividends. Firm beta and dividends. High growth firms are generally young firms with high capital requirements. These firms are considered risky, and therefore these firms have a positive relation with beta. So the firms with high growth have positive relation with the beta. Firms with high liquidity are also considered to be less risky, and therefore liquidity has a negative relation with beta. So firm beta with liquidity. Next, large firms are considered to be less risky than the small firms, and therefore size is considered to be negatively related to beta. Finally, a firm with high earnings variability is considered riskier, and therefore earnings beta is expected to have a positive relationship with the security beta. To summarize, in this video, we discussed some of the properties of security that are linked to beta. These include relationship between dividend payments and beta, growth and beta, liquidity and beta, size and beta, and finally earnings variability with beta. In this video, we'll introduce multi-index models. We'll discuss some of the basic properties of these models. An improvement over single index model is multi-index model. These models are often employed to explain and estimate the correlation structure of security returns. These models aim to capture the non-market influences that may cause securities to move together. That is, the movement or correlation across securities that cannot be accounted for by the market index itself. These multi-index models aim to capture economic factors or structural groups, for example, industry effects. The generalized multi-index model can be written in the form of this equation: Ri equal to Ai star plus Bi1 into I1 star plus Bi2 star into I2 star and so on up till Bil star into Il star plus Ci. What is the interpretation of these Ai star, Bi1 star and Ci1? In this equation, returns on security I is expressed as a function of indices I1 star, I2 star and so on up till Il star. Bij star is a measure of sensitivity of stock I to changes in index J, and that is why it is written as or noted as Bij star. Bij star has the same interpretation as that of beta I. Bij star is a measure of sensitivity of return of stock I to changes in index J, and it has the same interpretation as that of beta I in case of single index models. For example, Bij star of 2 means Bij star of 2 means that if the index changes its direction in a particular direction by 1%, whether increase or decrease, the stock return is expected to change by 2% in the same direction. This is similar to single index models. The stock specific component, again similar to single index models, the stock specific components, this AI1 star and Ci, these are stock specific components. Here AI star is the expected value of the unique return, a constant. This is the constant term. Usually one would expect this term to be 0. That is not significantly different from 0 in the regression model output. However, short-term investors, day traders, are often look out for securities with this kind of positive or negative alphas or alpha I stars. Often I refer to this alpha I or AI. The securities are considered to be underpriced or overpriced. However, one cannot expect a very high and significant alpha over long durations. Only to the extent trading costs prevent traders arbitrageurs from taking a long or short position in that security, the abnormal returns as indicated with this alpha I star or AI star that can sustain for a short term. That is, only to the extent trading costs prevent traders and arbitrageurs from taking a long or short position in that security, the abnormal returns indicated by this alpha can sustain. Any excess alpha over the trading costs will be swiftly exploited by traders and arbitrageurs. This alpha may also include a risk-free component of expected returns, and therefore advanced models adjust the expected returns with a risk-free rate to obtain or estimate this alpha, that is a more precise measure of risk-adjusted abnormal returns. Ci is the random variable with a distribution mean of 0 and standard deviation of sigma square, Ci. So this is sort of stochastic variable. The indices Ij stars, these Ij stars, the indices, they would capture the influence of market returns, level of interest rates, and various industry effects. While a model of this kind is often employed in the literature, it faces one major challenge. Some of the indices employed in the model may be correlated. This vitiates the estimation, as the regression estimations of this kind require the independent variables, that is all the independent variables Ij like I1 star, I2 star and so on, to be uncorrelated. However, when the variables are correlated, it is difficult to segregate their respective effects, that is Bij stars, on the security. And therefore, researchers often perform a procedure called orthogonalization to remove the correlated portion from the respective indices and create orthogonalized indices. That is, the original equation, which is this equation, through orthogonalization procedure, which is a mathematical procedure, is transformed into this new equation. The important point to note about this new equation is that unlike the original I1, I2 stars, which there was a possibility of these original indices to be correlated, the new indices that are created, that is I1, I2, I3 and so on, these are supposed to be uncorrelated. That means these new indices that are constructed, they are so constructed as to have no correlation with each other and the error term. So first and foremost, we can say that error term is not correlated with these indices, and that can be represented as this ij minus ij bar. So the expectations of ci into ij minus ij bar is 0, which suggests that there is no correlation between indices and this error term. And also these indices are so designed that do not have any correlation with each other as well. So the new equation, this is our new modified equation. This is our modified equation. In this equation, all these I1, I2s are expected to be uncorrelated with each other. And they are also expected to be uncorrelated with the error term, which is Ci. So for example, for any security I, this error term, residual term Ci is expected to be stock specific and therefore not correlated with indices Ijs. However, for this new equation, unlike the original equation where we would have said that I1 star is probably the market influence or I2 star is probably the influence of broad interest rate, here it is difficult to economically interpret the new indices. So the exact economic interpretation is difficult. To summarize, in this video we introduced multi-index models. We also discussed some of the basic properties. We found that these indices can be correlated, these economic indices, when they proxy economic variables like market influences like interest rate or broad market wide movements, they can be correlated. Through orthogonalization procedure, one can make these influences or indices uncorrelated and also uncorrelated with the stock specific components like residuals. However, the newly designed indices may not have exact economic interpretation and it may be difficult to interpret them. Design of multi-index models. In this video, we'll discuss some of the basic definitions, assumption and construction of multi-index models. The final general multi-index model can be defined as follows. This equation Ri equal to alpha I or Ai plus Bi1 into I1 plus Bi2 into I2 and so on up till Bil into Il plus Ci for all stocks I from 1 to n if there are n stocks, and j indices 1, 2, 3 and so on up till L. So there are total n indices, and here let's define the model. By definition, the residual variance of the stock I equal to sigma Ci square. So this is the stock specific component. The variance of index Ij is equal to sigma Ij square, which is the variance of index. So this is by definition. Next, by construction, we say that the means of Ci, the error terms in the model, the residual, this term, the mean of this term is 0 by construction. So regression model, to some extent, to a good extent in fact, regression model ensures that this property is held. We also assume that covariance, by construction, covariance between indices j and k, that is Ij and Ik, are not correlated, or the covariance between them is 0, which is this expectation of Ij minus Ij bar into Ik minus Ik bar. Remember, we discussed the orthogonalization procedure in the previous video where we said that the indices are so constructed that they do not have any correlation with each other. We also say that stock I and index j do not have any covariance or correlation, so the expectations of Ci into Ij minus Ij bar equal to 0. So this is also by construction. The way these indices are generated, not only they have no correlation with each other, they also don't have any correlation with error term or residual in the model. Last and a slightly more difficult term, that covariance between error terms CIA for security I and CJ for security J are not correlated. That means expectation of CI into CJ is 0. Now this is a slightly tricky term, as we'll see. This is the last assumption, that the covariance between CI and CJ is 0, is very important for multi-index models. It suggests that the only reason stocks vary together is because of their common relationship with the indices specified in the model, that is IJs. And therefore there is no other reasons two stock I and J should have a correlation, because all that is common to them is contained by these indices that we have modeled. So the remaining error term, that is CI, CJ, that are residuals or stock specific terms, should not have any correlation. However, there is nothing in the model that forces this to be true, including the regression model that also doesn't ensure that this relationship is held. And therefore this is only an approximation or sort of assumption, and the performance of the model will be as good as this approximation. To summarize, in this video we discussed some of the basic properties of multi-index model. We discussed some of the definitions and also some of the properties that are held by construction, and lastly some of the properties that are just assumptions only, and the performance of the model is as good as these assumptions are held in practice. Multi-index models, expected return and risk. In this video we'll introduce the expressions for expected return, variance and covariance for multi-index models. Similar to single index models, the following equations provide the expected returns, variance of returns and covariance between securities in the context of multi-index models. We can straight away translate those results. For example, for expected return, Ri bar equal to alpha I plus Bi1 into I1 plus Bi2 into I2 and so on up till Bil into Il bar. While the expression up till here is very similar to single index model, in a very identical fashion we introduce other indices and their sensitivities with respect to security I, that is Bi2, Bil and so on. So this is our expected return expression. Again, similar to the single index model, we introduce variance of return as sigma I square equal to Bi1 square into sigma I1 square and so on up till Bil square into sigma L square plus sigma Ci square. This sigma Ci square represents the residual or stock specific idiosyncratic component of risk which is specific to security I. The remaining components include one variance terms for the index which is included and the sensitivity of the security. So it is also very similar to the single index model where we had just one term which is Bi1 square into sigma I1 square. Now that we have L indices, we have Bil square into Bi sigma L square, so up till L terms. But again very similar to the variance of single index model. Lastly, we have covariance between security Ij, which is given as sigma Ij equal to Bi1 into Bj1 into sigma I1 square plus Bi2 into Bj2 into sigma I2 square and so on up till Bil into Bjl into sigma L square. And again it is also very similar to the single index model where we had only one term which is Bi1 into Bj1 into sigma I1 square, and in a very identical and intuitive manner we have introduced the covariance terms for other securities. Here for example Bi1 into Bj1 are the sensitivities of security I and J with respect to this index I, capital I and so on. So security I, security J and their influence with respect to this index I1. Similarly I2, J2 with respect to index I2, and similarly we have all the other covariance terms. So this is how we define covariance terms. Here we can clearly see that the expected return and risk can be estimated for any portfolio. If we have the estimates of alpha I, this one, and for each stock, Bik between each stock and the index, and an estimate of sigma Ci square for each stock, which is the variance of the stock. And finally an estimate of Ij bar, which is index specific, mean of the index, and variance of sigma Ij square, which is the variance of index Ij for each index. Assuming there are n securities and L indices, that results in total 2n plus Ln plus 2L estimates. For example, as an analyst, if you're following, let's say 150 stocks and 10 indices, then this means 1820 inputs. Generally, analysts start with the single index model, which is usually the market index, and then keep on adding industry indices. This structure, although it is slightly more complex than single index models, but is still less complex when no simplifying correlation structure is assumed. Please note that these industry indices are so constructed that they are uncorrelated with each other as well as with the market. The basic assumption here is that a firm's return can be affected by market and some other industries. Researchers often derive indices from the available data using quantitative techniques, for example, principal component analysis and factor analysis. One can add more and more indices to increase the explanatory power of the model. However, with more indices, the model becomes less efficient and more complex. So it's a trade-off between complexity, efficiency, and explanatory power of the model. To summarize, in this video, we discussed three important properties of multi-index model, including expected return, variance of return, and covariance between securities I and J. Lastly, we also discussed that in a multi-index model, addition of new indices can be done purely on mathematical basis. However, there is a trade-off. While you add more and more indices, you add to the explanatory power of the model, but at the same time your model becomes complex and probably less efficient. So while adding more or less indices and optimizing the model, there is a trade-off in terms of complexity, efficiency and explanatory power of the model. Multi-index models, three-factor Fama-French model. In this video, we'll discuss a very important model which is part of the multi-index model family. This is three-factor Fama-French model. To begin with, one very important model needs a special mention here, which is Fama-French three-factor model. In addition to market, which is this factor Rm minus Rf, the Rm bar is the market factor. Fama-French found that the size, which is proxied by market capitalization, and ratio of book to market have explanatory power on the cross-section of expected returns for common stocks. They documented that cross-section of expected returns are negatively related to size and positively related to book to market. So this small minus b is this second factor, which is size. That is, small stocks have higher returns as compared to large stocks, and high minus low book to market value. So here first factor is Rm minus Rf, which is the market index indicating the excess return over risk-free rate. The second factor is R bar SMB, which is small minus big, indicates the excess return on a portfolio of small stocks over large stocks. The excess returns by small stocks capture the fact that they are riskier than large stocks. So that is R bar SMB. And then R bar HML, high minus low book to market ratio, which indicates the excess return on a portfolio of high book to market stocks over that of low book to market stocks. That is, generally these high book to market stocks are also referred to as value stocks, and low book to market stocks are referred to as growth stocks. So the value stocks offer higher return as compared to growth stocks. Now the idea is that, for example, in the context of size factors, SMB factor, it appears that these indices, the size as well as HML, they represent some sort of risk factor. That is, small firms are argued to be riskier than large firms. Also, firms with high book to market ratio are considered to be undervalued or value stocks, like we discussed. Maybe market is more cautious about these value firms and prices are repressed, could be due to some significant changes happening in the organization. In contrast, firms with low book to market values are valued by market at a premium. For example, tech firms like Google, Microsoft, they often trade at a premium as market is upbeat about them. Therefore, on average over long horizons, high book to market firm offer higher returns as compared to low book to market firms. To construct the size factor, analysts compute the difference between small and large firms based on market capitalization. So that is our R bar SMB, small minus big factor. The second variable, defined as high minus low, is constructed using the difference in returns between the high and low book to market firms, which is value versus growth factor. To summarize this lesson, introduction of single and multi-index models considerably simplifies security analysis. In particular, the complex correlation structure between two securities is replaced by the common influence of the index on each of the security. With the application of these index models, portfolio analysis is considerably simplified. Portfolio betas are often less noisy and more informationally efficient than betas of individual securities. Construction of multi-index models broadly employs similar theoretical underpinnings, except that they employ multiple indices. Construction of these index models requires certain assumptions, some of which are held by the assumption, design, or definition of the respective model. Some of these key assumptions in these index models are as follows. First, idiosyncratic error terms are not correlated with indices that are more systematic influences, that is, expected value of Ci into ij minus ij bar equal to 0. Next, these indices are not correlated across each other. That means expected value of ij minus ij bar into ik minus ik bar equal to 0. The error terms are not correlated with each other. That means expected value of Ci into Cij equal to 0.